Yeah?
Yeah, why is there only one negative sign? Like there should be the negative sign before the other student also.
No, not this. This is the vector. So only the vector gets flipped to create the inverse, right?
So,
You don't flip the first one. Because remember, if I understand what you're saying why this does not get flipped?
yeah.
No, because, okay, let's look at this. Let's go back to the theory, which is right here, and see what the conjugate is of, or the inverse is. Yeah, there. See here? Q star is W, the same W, minus, minus, minus. It's just like when you have a complex number, right? Only the second part you flip, right, to get its conjugate. Yeah.
Get the value for V global, right?
Yeah.
Variable V global.
Yeah, you need to take the V local as your new input.
Not V global,
Like-
V global.
Yeah, right. You already have that answer, right?
So, like in the final output, our V global should be -1, 0 and 0, right?
The answer has to be this. Because we already transformed it to this, right? So I'm saying take this, do the reverse transformation, you should get back the original vector.
Yeah, that's what I'm saying.
Yeah, you get it? Okay. So I hope you got it. So essentially,
Have to change that.
we took this and moved it here, and all I'm saying is take this, do the reverse quadratic transformation and move it back here. That's it.
Yeah.
So that's confirmation that you understand how to use it. So it's a question of finding the quaternion for the reverse transformation. You know how to do that, right? The reverse transformation is either you can change the angle or you can just change the direction of the vector. Well, you actually know because that's how we got the original quaternion, right? So now if you're going to transform in the opposite direction, you know how to set up the quaternion. So, okay, so I want to show you something, just as a digression, because I have a doctoral student who's almost finished, who is working on multi-robot path planning. So you know when you have multiple robots, like in a warehouse, like Amazon has got all these robots that are delivering packages to the dock to go to different destinations. Then if you want the maximum throughput, because companies are always trying to do maximization of profit. So you want these robots to be able to go as fast as possible from wherever the packages are to the dock and back. And then you don't want them to collide with each other. So that's the nature of this application. So let me explain. So we have to compress the field. This can be expanded to any area. These are the three robots. You see they are misaligned. They typically have to go down here, and there is a final destination which will be evident once these robots make it to that point. I have the coordinates. She's writing a paper. So she should really have marked the final spot. She didn't do that. But essentially they will somehow, without hitting each other, get to their destinations. So let's play it. If necessary, we play it again. So there's a near collision, but it's not going to happen because, see right there? Whoa, that was pretty close. It's pretty nicely chosen, the experiment. And it also missed the garbage can. Let's run it again. So she made a good choice of the experiment because it's very convincing. Something happens, you know, it flips back the moment you play it. Right now it looks upside down. So it's a narrow escape. Almost all three at some point, see those two are almost colliding there. And this one is almost colliding with this. And the destination points are somewhere here. So in a warehouse, you'll have this situation of trying to optimize the flow. These are all autonomous. It's a nice area if you want a job that you're interested in as opposed to just collecting the money and you hate the job. Let's move to localization and mapping. So the plan is localization and mapping, roughly 2 hours of it, maybe less. If we get tired, we'll quit. And then next week, I'll finish off localization and mapping. It'll take most of Saturday. And then we'll start the last topic, the big one, cognition. And then there's a sensing and perception topic. That's kind of short, 2.5 hours. So we'll wrap it up between Saturday and Sunday of next week. Okay, I hope I posted everything correctly. Let me double check. Yeah, this is what I want. It seems like ages ago, that introduction, which I did from remote, where we introduced the different sub-areas of robotics. Well, here is a chance to refresh your memory, because when you get into the forest, which is the details of the course, you should never lose sight of what the forest looks like from 30,000 feet. Because otherwise you have no context. You're going through these topics and you don't understand the relationships. So this will help you refresh your memory on that. So let's say that some kind of intelligent navigation is being planned. So navigation based on planning that involves going to desired destination while avoiding obstacles. So simple thing that all mobile robots have to do, right? Here are the building blocks, and that's what I meant by the sub-areas, sorry. First you got to understand the environment, right? So you don't even move till you look around you and you sense and you perceive. Sensing and perception, the last topic, though it should really be the first topic actually, because that's the first thing you do, right? So I look at this class and I'm able to see where you are. So that's like, I take the data and I make some sense out of it. So you need to do that before you move. Then you need to know where you are. So you have a map, or maybe you're going to build one as you go, but you have to know where you are within the map. So that's localization and mapping, the topic we're going to take up today. And then after that, you say, okay, I know the map, I know where I am, I know where I have to go, I'm going to figure out the best path. So that is coordination. That's not the only thing you can do with your brain, but almost all mobile robots have to do that, right? You have to navigate intelligently. So that's the example we're going to use when we get to the cognition topic. So most of the time cognition is path planning and navigation. And then you got to do motion control, right? And how do you do motion control? Because you have a model of your robot and you know how it feels, and then you can drive it. Remember the exercise I gave you, the C? So you know how your robot feels when it moves, and then you try to drive it on a path. So these are the different sub-areas of robotics. So never lose sight of that, because the details you often forget, but the big picture you have to remember. If you go for an interview, knowledge starts with this. Quaternions is a detail, but this is the big picture of robotics. So assumption, the robot needs to move from current location to desired location to fulfill the mission. That's the assumption. So using a pre-developed map to accomplish this task requires robot to establish its pose. That means, remember at the beginning I said a map is no good unless you can localize within it, right? And if you know your location, then it's useless if you don't have a map. Because somebody tells you you're on this point on the earth and says you need to go here, but you don't know where you are on the map, then go there has no meaning at all, right? If somebody says go to your grandmother's house and you don't know where you are, then how are you going to go there? Because you have to localize yourself in the map in order to get to your grandmother's house. So this mapping and localization can happen in any order. So if robot knows its pose, meaning that x, y, theta, right? Then the first thing you do is, at least your sensors on board enables you to see for a certain distance. That is known as the sensor horizon. So all robots have at least a local map, right? The moment you turn on your LiDAR camera and all that, you can see up to a certain distance, right? You can't see the whole campus, but you can see up to a certain distance. So the first thing you do is you take that local map and put it on the world frame. And then the adventure begins. As you move, you are facing this way, as you move, you see more and more on the campus, and you keep putting it with the right alignment, right? That's why you need coordinate transformations and so on. Otherwise the map will be all mixed up. So even though it appears to be the classic chicken or egg, which came first, chicken or egg, it doesn't matter. You can start with localization or you can start with mapping. So either will work. So very often map development happens as the robot explores. Now yes, we have Google Maps, right? But the Google map is not the correct map, because for one thing, it does not tell you where the moving obstacles are. So it's for you to figure out where the other cars are, right? It just gives you general directions. But you have to figure out where the other cars are. Also, if the animal has come on the freeway, Google doesn't know anything about that, right? If there's a water main break and there's water going across the road, they don't know about that. Even accidents, there's a delay before the Google figures it out. They'll tell you that there's a delay here because of an accident, but it takes minutes, right? They're trying to speed that up. But If the accident happened just then, you're already in the congestion. It's too late because Google, does not reroute you. So the way, the technique used to localize and map is known as SLAM. So SLAM stands for simultaneous localization and mapping. Any one of those can begin first. Localization first, then mapping, or mapping first, then localization. Once you start, localization mapping. As you move, you see more, right? You put it on the map, and then you localize yourself, and one after the other. All right, now some facts about maps. That's pretty much what this information is. You have both global maps and local maps, right? So I have a map of this class in my head right now. But this is a child, right? The parent would be this entire floor. And then the floor would be the child of the entire building. And the entire building would be the child of the campus, right? So you see this hierarchy? We're not interested in the map outside the campus right now because we're not intending to go outside the campus, right? But if we were, then the campus becomes the child of, the surrounding area, right? And then we have the whole of Tamil Nadu. And then we have the whole country. You see how it works? So you never need to know the whole world's map at any given time. But you just have a parent-child relationship based on what you're interested in. So campus map is a local map. What the robots see is very local. So the sensors are seeing a very, very local map. That is the rawest map that you can get. It's called the sensor horizon because LiDAR might go up to 80 meters, right? And that's it. You can't see beyond that. So that is your first map, that local map. And then the prior map, even a Google map, may not be fully reliable due to recent changes, accidents, water main break, road repair. Typically the road repairs, Google picks it up. Mistakes in map creation. So there can be a mistake. There was an accident described. I don't know the details because I don't have the link. But somebody took a left turn onto a bridge and the bridge was actually, broken. They went right off into the river and died. And they're suing, I think the family is suing Google now. Because Google said go this way, and they went and fell off the bridge. Definitely, when you have an earthquake or a battlefield zone, no way the map is going to be useful. Any map before in a battlefield zone, everything's going to be blown up. Earthquake? Oh, absolutely not. I saw some, in US we have these tornadoes. So the wind goes in a circular pattern. It picks up entire houses and throws it in the air. Animals are thrown up, and they're found on trees and all that later, cows and all that. So if you look at that, no map. People say my house was in this intersection, and they can't even recognize it because everything has changed, right? Because how do you find your house? You look at the landmarks around it. Yeah. So the house, they can't even, because they're going there to collect photographs and some personal belongings. But first they have to find the house, and it's so difficult because the whole landscape has changed. So they don't even recognize their house until you use some GPS or something. And of course, if animals or other cars are moving in and out, then you have to somehow dynamically refresh the map. And the thing is, a moving obstacle can't be left on the map, right? Because then your map will be filled up with obstacles that are no longer there. They have driven by. So there is a very clever system whereby you keep sampling a space. And if the car is there, it's there. But after the car goes away, you're sampling nothing, so you cancel it. So maps are augmented and the opposite. Otherwise you fill up the whole space. Okay, so you don't need to go to that. That's the tiny font is basically this document called SLAM for Dummies. Obviously the authors are making fun of themselves. There are many for dummies books. You may have come across them. C++ for dummies. It doesn't mean that the people reading them are dummies. They're just making fun of themselves. That's all they're doing. So SLAM for Dummies is not the Dummies series of books, but it's an MIT tutorial written by a couple of guys on what SLAM is. I'll show you what it is. We don't need to go there. Alright, so this is how SLAM works. I told you, there's no point in knowing code. If you jump into the code without knowing the qualitative solution, it's backwards. You have to first understand what is being done. So here's the robot, and here are 3 landmarks. So what the robot does is, maybe it uses LiDAR and gets the position of that first landmark, the second landmark, and the third landmark. So you can think of them as lightning bolts, you know. So you go grab them, and then you put them on your local map, because I assume that the localization is available first. So based on the localization, it puts these three on the map. Is it okay? So robot is represented by a triangle. The stars represent landmarks. The robot initially measures using its sensors the location of the landmarks. Sensor measurements are illustrated with lightning. Okay. Then the robot starts moving. These have not moved, right? They are in the same place. So how do you measure where the robot is now? The robot moves as it now thinks it is here. It now thinks it is here, and that's through odometry. So that's not the exact position of the robot, right? It's odometry telling you the robot is there. And you know odometry has some error. So odometry will fail eventually, but we're not going to let it fail, because the position is going to be corrected. Based on what? We're not using GPS. SLAM typically does not use GPS. SLAM is meant for indoors. It can be used outdoors also, but typically it's used indoors. So we're going to use SLAM here to correct the odometry. So lightning bolts again. Now, there is a detail that is left out in this description. How do you know that this obstacle that you saw from back there is the same as this obstacle? Now, what if they are traffic barrels? They all look alike, right? So there is a technique known as scan matching. So you can identify, okay, the one I saw here, it's got to be this one. The one I saw over here, it's got to be that one. You can do that. There is a mathematical algorithm. It's not perfect. So sometimes it will make mistakes, right? But suppose you have 5 barrels and you make one mistake, it's okay, because the other 4 correct identifications will save you. So you have 2 other things happening. When you move, new barrels are coming in, right? Let's say you're moving through traffic barrels or an earthquake zone. So maybe you're getting a new landmark. So you have to know it's new. You shouldn't be identifying with something that's already there, right? So you have to be careful about that. Also, things that were in the vision field have now moved out. So you got to know which ones moved out. Maybe barrel A moved out, right?
Yeah.
So it's a very complicated algorithm. The scan matching algorithm is like separate to SLAM. Somebody came up with that. If you don't have a good scan matching algorithm, then you're going to make a lot of mistakes. Okay? So you need that as a part of your SLAM algorithm. I'm sure, libraries have that already. So you don't have to write it from scratch. So what if you don't have any barrels? Well, if you don't have any barrels, if it's just an empty room, you can't do SLAM. SLAM requires features. So you can't do SLAM on the ocean. You know why? Because the ocean, everything looks alike, right? Waves form and disappear. So there's no permanent landmark, right? Same thing in the desert, right? Most deserts, like the Arizona desert is different because you have these cactus trees, right? But if you go to the Rajasthan desert, it's just sand. So you can't do SLAM there.
Even in forests.
Huh?
Forests as well.
Forest, the same thing. Everything looks the same. So that's why SLAM has to have features. Now, what about long corridor in a building? Can't do SLAM. Except maybe people have hung pictures on the walls. And hopefully those pictures are not the same person. If you put the picture of the same person, they're all going to look alike, right? But if they're different, you can use that for SLAM. And you can use a regular camera for that, not a LiDAR. Okay, so the robot thinks it is here because of odometry, but we want to correct it. So I take sensor measurements again with your LiDAR, and I can figure out where you are. The robot once again measures the location of the landmarks using its sensors, but finds that they don't match with where the robot thinks they should be. Thus the robot is not where it thinks it is. So if you look at the odometry, you won't agree with the sensor readings. That's what he's saying. If you go with the odometry placement, right, and your sensor readings, there'll be a mismatch. You agree?
Yeah.
Because the odometry is telling you you're somewhere else. So you have to resolve the two together. That's what SLAM is. There it is. The robot is actually here. Odometry is telling you this, you're actually here by the LiDAR measurements. Now, do you go with both positions? Do you average two positions? No. There's a technique known as Kalman filtering, which finds the best compromise. If you believe your LiDAR more, which one would you choose? You would choose a LiDAR. If you believe your odometry more, which one would you choose? The odometry. But typically, both of them are speaking the truth, but to a different extent. So you have to have an algorithm that merges them. Averaging is not good. Averaging means they are both equally in error. But they're not equally in error. The odometry is actually much worse than the LiDAR, right? So there has to be a statistical technique of sensor fusion. And that's what is done in SLAM. And you see, now this is the robot. And that's it. That's basically SLAM. All the rest of it is details. It's got a lot of material for details. Then you have to write, SLAM algorithms are already there in fact, yesterday we showed a demo of G-mapping, basically SLAM. It's already there in ROS. So typically SLAM is used in applications where GPS is not available, which means indoors. Now you might use SLAM in New York City, because in New York City, because of the tall buildings, GPS is often, and not often, but quite a bit at fault. Because it creates multiple paths, and so there is some confusion caused by GPS when you have tall buildings nearby. So then SLAM is an additional help. So SLAM is difficult to use in obstacle-sparse environments like ocean or desert. I already mentioned that. Generally, you get environmental features indoors. There are also algorithms that integrate SLAM with GPS. So this is something I may have mentioned yesterday. You don't just overdo it by doing SLAM plus GPS plus odometry and IMU because you have it on board, right? Doing both. Doing everything, in fact. No, because the cost goes up.
Yeah.
The competition time goes up. So you never build more into the product than the customer would pay. You just try to achieve the target. There's no point in overdoing it. For fun, you do all kinds of things in university labs, but you can't sell a product if you put too much into it. So that's what GPS-aided SLAM is there. It's a special algorithm, an improvement. So in urban areas, you might use this. When you have a high-rise, a lot of high-rise buildings, like in New York City, you have a problem with GPS, so they throw in SLAM. So GPS also has other problems apart from the high-rise building problem. There are outages. It's rarer now. In the old days, it used to be more frequent. But I was reading a newspaper report where President Putin was claiming that they have the technology to jam all of Elon Musk's Starlink satellites. Apparently, in the event of a war, they can jam all of them. Now, maybe he's bluffing. But I'm sure somebody will figure out a way of jamming that, and so then you'll have no GPS. So what are you going to do? You have to have other measures, because so much of war depends on GPS now. Knowledge of GPS. Also, GPS has less than desirable accuracy. So the very first GPS used to be something like 5 to 10 meters, and 5 to 10 meters is okay if somebody is saying take this ramp. Take this exit, right? 5 to 10 meters is okay because you're also going to be reading the sign of the exit, right? So 5 to 10 meters is enough. Then it came down to 1 meter. But think about a robot going next to a swimming pool.
Yeah.
1 meter is too much inaccuracy. The robot could, if the robot is not properly sealed against water, it's going to fall in. So everything is relative to the application. Nowadays we have sub-centimeter GPS. Yeah, quite accurate. But you have to, it's costlier. So GPS, as you know, does not provide orientation, only a position, and if you move, then you can figure out the orientation. You have to move, and then with successive GPS points, you can figure it out. And as I said, you have GPS-aided SLAM, but you also have others. VSLAM is visual SLAM, that means camera. So the cameras used, maybe you can use LiDAR and odometry and the camera. So V comes from the visual, traditional camera. It looks at obstacles in the environment and it figures out. So that's another sensor value to fuse. This is multi-sensor fusion, that's what it is. So you throw in a camera, it's just an extra thing to fuse. And then Wi-Fi SLAM is available. It's not common, but it's available. Several years ago, there was a lady in the middle of winter, driving in the dead of winter. Car went off the road into deep snow, but her cell phone was still alive. And so somebody reported her missing, and after a while, they were able to find her position from the cell phone towers. So you can say that that's like a Wi-Fi SLAM, because they located her and saved her life. There's also more recently something called Bluetooth real-time location systems. It uses Bluetooth in a SLAM mode. I hope this company is still around. You can go to it. I haven't gone there recently, but within a room, right? All of your phones have Bluetooth, so it is possible to locate you. Maybe you're in a party, a big party, and it's possible to locate you where you are. So companies can locate you. I don't know whether you want that, your company monitoring where you are every single moment of the day, but they can locate you using your Bluetooth signal if you give permission. That's the same SLAM thing. The only, the dummies book, they're basically similar figures, but these are the original two SLAM papers. Hugh and White and Tim Berry. I think one of them is a student. I could be wrong. Maybe about faculty, but not so long ago, less than 20 years ago, they came up with SLAM, and now it's pretty standard in many localization. And so this is dealing with the challenge of localization. What are the big problems in this area? So of course, the job is to find the absolute pose of the robot. That's what localization is. What is the XY theta? For a drone, it is 6 numbers, right? X, Y, Z and 3 angles. So it gets more complicated for a drone. The problem is, it might not always work as desired or even be feasible. Outdoors, you have GPS, and we already talked about the outage problem. What if you go into a tunnel? Nobody's going to be hanging pictures in a tunnel. Remember I said, if pictures are hung in a tunnel, in a hallway, then you can localize yourself. Well, tunnel typically doesn't have that. Maybe here they'll put pictures of politicians in a tunnel. I'm joking, but you get the idea. It's typically there. So what do? So you have to wall follow, right?
Yeah.
Wall following is an excellent way of localizing, isn't it? So till you get out of the tunnel, you just follow the wall. And so when you get out, you get back your GPS. So in the self-driving car movement, all these things are being tried, because you can't have a self-driving car unless there is near perfection. You can't get perfection, but you have to get to better than human driving. You're saying why? Is it enough if it's as good as a human being? True. This is a big debate in the US, right? When a machine kills a person, it is considered more serious than a human being killing a person. So even if the machine functions as well as a human being, if a machine kills a person, you will be sued and lose a lot more money in court, because it's considered more serious. Like a machine killing a person is different from a human killing another human being. So I was this was less than 10 years ago, I was in the outskirts of Munich. There is a place known as Dachau. You may have heard about it. There was a Jewish concentration camp. One of them was at Dachau. So I visited the concentration camp, and then I was having lunch in the city of Dachau, and I started talking to some guy who looked like he had been at a conference, and he was saying he was at a conference. It turned out our areas were quite related. He was at a conference where they were trying to figure out rules. If you have a self-driving car, right, they project that if it's about to fail and crash, that it will have some last few milliseconds, hundreds of milliseconds of decision making, right? And they project that in the future, everybody will know everybody. The self-driving car will know that, oh, here's a 90-year-old guy on this side of the road. Here is a baby in a pram on the other side. So if I have a little bit of control, will I choose to kill the baby in a pram, or will I choose to kill the 90-year-old guy? And no, the answer is not the 90-year-old guy. So I'm not anywhere near 90, by the way. So you can pick the 90-year-old guy if you want. So it's a very complicated question, and they want those all answered legally before a self-driving car ever gets on the road. They want to know, because of the last few. See, when a human being crashes, you don't think of, okay, I have a few moments of control, will I hit this guy or this guy, right? It's all over. But a machine, it has all that code running on it. So maybe it can be forced to steer this way or this way, right? So how will you make that decision? That's the ethics people are actually, they have conferences and they publish papers on this. The other related issue is, if you have a self-driving car, why should you pay insurance for the car, right? The insurance is because you're going to hit something, right?
Yeah.
But if you're not driving, then why should you even pay a single dollar of insurance? So that debate is also going on. Who should pay for it? Should the manufacturer pay for it, or the government, or how is that going to be resolved? Okay, now, so as I said, GPS may not be enough accuracy, and in the early days, it was only going at about 1 hertz for the earlier systems. Now it's a little bit faster. You'll be surprised to know this. Indoors, there's a GPS-like system. You can check because companies go out of business and come back. There's 2 of them: the Cricket indoor location system and the Stargazer robot localization system. We have some version of this. So we have a unit that actually allows you to localize within a hallway. And if you're prepared to buy more copies of them, you can extend the space. So yeah, so you can run indoor robot research experiments because GPS is not available indoors, so you can't.
Ceilings, they mount on the ceilings.
Yeah, they mount some beacons, on the walls, and you can localize within that area. So if you have a bigger hall, then you have to mount more copies of them. So why did I mention that? It's because it's similar to this. So where would they use this? So people have dementia or Alzheimer's, and if they are in a facility where they're being looked after, you don't want to chain them to a chair or something, right? Because that affects their quality of life. So you want them some freedom to wander around the grounds, but you don't want them to go out the gate because there might be traffic outside, right? So the moment because these are people with Alzheimer's, they really don't know what's going on. So this is the way they try to track them. So they have a system whereby they can, there's a central station, or maybe there's a computer program which alerts, this guy is, very near the gate, we better stop him, and then somebody will go and get him. So they have the system in many of the more recent constructions. It's harder to build in this kind of a system in an older building. It's better to design the building with all these already there. So, some of the more modern, fancy hospitals, they're thinking in terms of things like this. Now, I mentioned the Detroit Free Press printing facility because about 15 years ago, it was one of the most modern printing plants, and it had automated the process of picking up bales of paper. Paper is going out of business. Like, I'm surprised that people order the Hindu and the Indian Express because their paper is completely, like, nobody reads the newspaper as in paper form.
Yeah, here it's a different
Except the
emotion.
oldest guys, huh?
It's a different emotion.
Right. They want to, sit with their coffee and read it, right? So over there, we had this Detroit Free Press. It may have gone out of business because nobody's reading the print version, but bales of paper had to be brought from the dock to the press. So this was regular. Throughout the night when they were printing copies, you would have these big vehicles, indoors. So what they had done is, they had designed the printing press with a very ordered system of lights. And so the robot was using those lights to localize. So it knew the intersections and the turns and so on to get to the dock and back to the machines. They had many machines, right? Because they are printing thousands of copies. And it was using the light system to localize. It also had a LiDAR so that if one of the employees walked across, it would stop because they demonstrated this to us. And then it would continue, and then by looking at the lights, it knew the turns. And it was quite nice to see, actually. So that's very simple because you have a controlled environment. Self-driving cars in the worst possible environment, right? So it's faced with so many challenges. So that problem is not going to be solved anytime soon. Don't hold your breath, because no matter what Elon Musk says, the self-driving car is not going to be available for the next, I would say, at least 10 years. It's not going to happen. So it's better to, instead of retrofitting, it's better to build new buildings with this feature. It's the same thing, with Wi-Fi. It's kind of built into the newer buildings, right? Just like Ethernet used to be built in, but nobody uses Ethernet anymore. So it's all Wi-Fi. So if your GPS is not that great, then you have to use a landmark-based system inside a tunnel. As I said, follow the walls, ceiling light. That's what the Detroit Free Press is: ceiling light fixtures. And as I said, you may or may not want to map. If you don't want to map, you just throw away a local map. If you want to map, you take and put it on a word frame. That's the only difference. It's not easy though. If you have this much of turn error, you're going to be putting it all over the place. You get it?
Yeah.
The turn error is very hard to overcome. So you can't create a map unless you have precise turns. So if you can't do that, you just throw away a local map, because you say, I don't want to build a map, right? It's just for me. I navigate through. I say forget it, right? But think of this: if a robot is going through a battlefield, right? Should the second robot also have to figure out a path? If you've already gone through the battlefield, shouldn't you give it a map? And then it'll be easier for the second robot. It can go much faster. So those are the considerations for why you would develop a map, as opposed to I don't care. I'm just going to go through and forget about it. So this is the challenge of localization in the implementation side. Now some of these might be very new to you. This sensor noise, everybody's aware, right? But I want to give you concrete examples of what I mean by that. So noise is genuine information being speared with additional stuff that really is not relevant, but it's there because it's a fact of life. There's no such thing as a pure sensor signal. It's never going to be in this world, right? So examples are that if you have a scene, if you've got a camera focused on a scene in sunny versus cloudy conditions, it's the same scene, right? Now this is the same scene too, right? But you can think of this as noise, right? Right? It's the same scene, but my eyes see it differently.
Yeah.
So the same thing with the camera. If the clouds come over, it so happens that the cloudy conditions are the best for vision. If it's sunny, you get shadows and all that, and you get a glare. But the same scene can look different. So that's what is meant by the first bullet here. Suppose there's a raindrop on the lens. It's still the same scene, but the raindrop on the lens can cause distortion. What if the sensor mount is vibrating like this? Because the screw is loose. That's noise too. The scene hasn't changed, but your perception of it is changing because of the vibration. So this is why you need more information than the bare minimum. Human beings know how to use extra information, right? When we drive, we sometimes have too much information. But we know how to handle that. We turn left and right, cars going all over the place. Somehow we manage to figure it out. We have so much information, but because we have more than needed, we are okay. So the task is to get the computer to also use redundancy. That means information that is too much, but you use that to firm up your belief in anything, right? If you have more information than you need, you can use that to strengthen your decisions about what you're actually seeing. Now, we don't think in those terms because everything is automatic in our head, but a computer has to think in those terms. And as I said, you can't give it 10 times the redundancy because then the product becomes too expensive. You have to do just enough so that you can get the problem solved. Otherwise, the customer will not pay for it. Okay, second one, this name may not be familiar to you. So aliasing is if I pass myself off as someone else. So if I pass myself off as someone else, maybe I wear a mask that makes me look like Rahul Gandhi. So I'm aliasing. Okay. Now, what is the importance of that in the context of robotics? Objects that we see are not unique. I'm not talking about twins. I'm talking about physical objects. Now, I bet you there are multiple chairs that look exactly like this, right? This one, these two look exactly alike. So traffic barriers look alike, right?
Yeah.
Many restaurants, like particularly in the US, not so much here, but a Kentucky Fried Chicken is designed by the franchise to look the same from the outside, right? McDonald's looks the same. So how will you tell the difference if you're using it as a landmark? You can't. Your camera turns on and says Kentucky Fried Chicken, but this could be Kentucky Fried Chicken number 2 on the same road. So that's what is called aliasing. right? Those look alike, particularly when it's dark. Barrels look alike. Restaurants have similar frontage. A maze, do you know what a maze is?
Yeah.
Let's pull up because it's a very interesting robotics problem. If you want to create a maze in gazebo, you can, and you can try to get the students to come out of it. It's a very complicated maze. It's a simple maze. So typically the idea is you enter, and then you find the only exit. There's typically only one entrance and one exit, and you have to. So at that level, you can't see the exit, right? That's the whole point. They have the high walls. Some of the mazes are created by hedges, right? Hedges, vegetation. So you can't see over the hedges. So pretty much you can only come to an opening and you can say, should I continue straight or should I take the right turn? Apparently there's a maze algorithm that says that you explore each, right? But then you take the right turn. If you go to a dead end, you come back and take the right turn, right turn, right turn, right turn. And apparently that will get you out of the maze. Or you go left, 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 left. You can look it up on the internet. So the algorithm is keep taking the left turn. If you take left and right, you might be circulating there forever.
Yeah.
So that's how you get out of the maze. Now, there are some mazes. I even read a story years ago where they had a maze made up of hedges. And some people are very panicky. They want the challenge of the maze. But then after 1 hour, if they're roaming around and they can't get out, they almost faint. Some people are built that way. They start to get into a panic. So they have, in those kind of mazes with hedges, they have a person watching from a control tower. And once they get into that state, or they say, please, tell me how to get out, because they can see the entrance and the exit, and they can see the path. So they actually tell them, take a right turn, left turn, they get them out. Because otherwise they tend to panic, some people. Same thing with people who are trapped in elevators. They can't stand that. Okay, so point made. Let's move on. So a maze, everything looks alike, right? So how are you going to get out? You have to have some kind of algorithm. So typically in a maze, you wall follow. You want a robot to get out of a maze. There are competitions that do that. So the robot has to follow the wall, find the openings, and get out. So a maze is basically everything is aliased. Now, did you know this? You know about sensor aliasing, right, and sensor noise. But did you know this? Because lots of these things I did not know when I was growing up. Like I told you yesterday that the V equals U plus AT. I thought that was a description of reality. It's just a model, right? Because V equals U plus AT, you said, okay, that's the equation of motion no matter what the conditions are, right? But the fact is, the acceleration cannot be held constant in the real world. So, it's just a model, that's what it is. Now, the actuation noise, if you take a robot and give it the V omega command, right? See where it ends up. Pull it back to the starting position. Give it the same V omega command. Pull it back. Every time, it's going to end up in a slightly different position. It'll never be in the same position because the tires are gripping the ground, right? And there's always going to be some difference. There's going to be slips. And because of that, it's going to end up in a slightly different position. No, when we are young, we are trained to believe that the robot, given the same command, will end up in the same spot. It doesn't. So that's the nature of the real world. Now, if the battery gets weak, it will definitely not end up in the same position, right? If you do this all day, as the battery gets weaker and weaker for the same V omega command, the motors are not going to have the same torque because the battery has become weaker. So that is the real world effect that you have to take care of in your navigation algorithms. And of course, when we are driving, we compensate because we are looking where the car is going, right? So if this amount of turn is not enough, we turn some more. That's what a computer program has to also do. So basically, feedback is needed. You have to pay attention to feedback in order to get the system to do what you want. So here, the main point is localization does not have to be absolute. Localization can also be with respect to something else. So this is a famous researcher, Vijay Kumar. He works for the University of Pennsylvania, and they have a lab called the GRASP Lab. It's one of the best robotic labs in the world. So we're going to see some of the work of his PhD students, where they fly drones in close formation indoors. Okay, and the important thing is the drones have to be spaced apart, which means that they're localizing with respect to another drone, right? They don't have to absolute localize, they just have to localize with respect to another drone. So localization doesn't mean absolute all the time, it's the application that determines. So let's watch this after the commercial exploitation. Okay, there. Yeah.
Good morning. I'm here today to talk about autonomous flying beach balls. No, agile aerial robots like this one. I'd like to tell you a little bit about the challenges in building these and some of the terrific opportunities for applying this technology. So these robots are related to unmanned aerial vehicles. However, the vehicles you see here are big. They weigh thousands of pounds, are not by any means agile. They're not even autonomous. In fact, many of these vehicles are operated by flight crews that can include multiple pilots, operators of sensors, and mission coordinators. What we're interested in is developing robots like this, and here are two other pictures of robots that you can buy off the shelf. So these are helicopters with 4 rotors, and they're roughly a meter or so in scale and weigh several pounds. And so we retrofit these with sensors and processors, and these robots can fly indoors without GPS. The robot I'm holding in my hand is this one, and it's been created by 2 students, Alex and Daniel. So this weighs a little more than 1/10 of a pound. It consumes about 15 watts of power, and as you can see, it's about 8 inches in diameter. So let me give you just a very quick tutorial on how these robots work. So it has 4 rotors. If you spin these rotors at the same speed, the robot hovers. If you increase the speed of each of these rotors, then the robot flies up, it accelerates up. Of course, if the robot were tilted, inclined to the horizontal, then it would accelerate in this direction. So to get it to tilt, there's one of 2 ways of doing it. So in this picture, you see that rotor 4 is spinning faster, and rotor 2 is spinning slower. And when that happens, there's a moment that causes this robot to roll. And the other way around, if you increase the speed of rotor 3 and decrease the speed of rotor 1, then the robot pitches forward. And then finally, if you spin opposite pairs of rotors faster than the other pair, then the
So you realize the V omega and how we calculated, how we translated to the right wheel speed and the left wheel speed? This is much more complicated because the motion is being mapped to the individual rotors, right? But probably the equation's already there, and a roboticist does not have to worry about it. But it's still very complicated to come up with this.
Robot yaws about the vertical axis. So an onboard processor essentially looks at what motions need to be executed and combines these motions and figures out what commands to send to the motors.
That's what I meant.
600 times a second. And that's basically how this thing operates. So one of the advantages of this design is when you scale things down, the robot naturally becomes agile. So here, R is the characteristic length of the robot. It's actually half the diameter. And there are lots of physical parameters that change as you reduce R. The one that's the most important is the inertia, or the resistance to motion. So it turns out the inertia, which governs angular motion, scales as a 5th power of R. So the smaller you make R, the more dramatically the inertia reduces. So as a result, the angular acceleration, denoted by Greek letter alpha here, goes as 1/R. It's inversely proportional to R. So the smaller you make it, the more quickly you can turn. So this should be clear in these videos. On the bottom right, you see a robot performing a 360-degree flip in less than half a second. Multiple flips, a little more time. So here, the processes on board are getting feedback from accelerometers and gyros on board and calculating, like I said before, commands at 600 times a second to stabilize this robot. So on the left, you see Daniel throwing this robot up into the air, and it shows you how robust the control is. No matter how you throw it, the robot recovers and comes back to him. So
That's
why build
localization.
robots like
That's
this?
localization.
Well, robots like this have many applications. You can send them inside buildings like this as first responders to look for intruders, maybe look for biochemical leaks, gaseous leaks. You can also use them for applications like construction. So here our robots are carrying beams, columns, and assembling cube-like structures. I'll tell you a little bit more about this. The robots can be used for transporting cargo. So one of the problems with these small robots is their payload carrying capacity. So you might want to have multiple robots carrying payloads. This is a picture of a recent experiment we did, actually not so recent anymore, in Sendai, shortly after the earthquake. So robots like this could be sent into collapsed buildings to assess the damage after natural disasters, or sent into reactor buildings to map radiation levels. So one fundamental problem that the robots have to solve if they have to be autonomous is essentially figure out how to get from point A to point B. So this gets a little challenging because the dynamics of this robot are quite complicated. In fact, they live in a 12-dimensional space. So we use a little trick. We take this curved 12-dimensional space and transform it into a flat 4-dimensional space. And that 4-dimensional space consists of X, Y, Z, and then the yaw angle. And so what the robot does is it plans what we call a minimum snap trajectory. So to remind you of physics, you have position, derivative, velocity, then acceleration, and then comes jerk, and then comes snap. So this robot minimizes snap. So what that effectively does is produces a smooth and graceful motion. And it does that avoiding obstacles. So these minimum snap trajectories in this flat space are then transformed back into this complicated 12-dimensional space, which the robot must do for control and then execution. So let me show you some examples of what these minimum snap trajectories look like. And in the first video, you will see the robot going from point A to point B through an intermediate point. So the robot is obviously capable of executing any curved trajectory. So these are circular trajectories where the robot pulls about 2 Gs. Here you have overhead motion capture cameras on the top that tell the robot where it is 100 times a second. It also tells the robot where these obstacles are. And the obstacles can be moving, and here you will see Daniel throw this hoop into the air. Well, the robot is calculating the position of the hoop and trying to figure out how to best go through the hoop. So as an academic, we're always trained to be able to jump through hoops to raise funding for our labs, and we get our robots to do that. So another thing the robot can do is it remembers pieces of trajectory that it learns or is pre-programmed. So here you see the robot combining a motion that builds up momentum and then changes its orientation and then recovers. So it has to do this because this gap in the window is only slightly larger than the width of the robot. So just like a diver stands on a springboard and then jumps off it to gain momentum, and then does this pirouette, this 2.5 somersault, and then gracefully recovers, this robot is basically doing that. So it knows how to combine little bits and pieces of trajectories to do these fairly difficult tasks. So I want to change gears. So one of the disadvantages with these small robots is its size. And I told you earlier that we may want to employ lots and lots of robots to overcome the limitations of size. So one difficulty is how do you coordinate lots of these robots? And so here we look to nature. So I want to show you a clip of Phenogaster desert ants in Professor Stephen Pratt's lab carrying an object. So this is actually a piece of fig. Actually, you take any object coated with fig juice and the ants will carry them back to the nest. So these ants don't have any central coordinator. They sense their neighbors. There's no explicit communication. But because they sense the neighbors and because they sense the object, they have implicit coordination across the group. So this is the kind of coordination we want our robots to have. So when we have a robot which is surrounded by neighbors, and let's look at robot I and robot J, what we want the robots to do is to monitor the separation between them as they fly in formation.
So that's
And then
localization.
you want to make
basically.
sure that this separation is within acceptable levels. So again, the robots monitor this error and calculate the control commands 100 times a second, which then translates to motor commands 600 times a second. So this also has to be done in a decentralized way. Again, if you have lots and lots of robots, it's impossible to coordinate all this information centrally fast enough in order for the robots to accomplish the task. Plus, the robots have to base their actions only on local information, what they sense from their neighbors. And then finally, we insist that the robots be agnostic to who their neighbors are. So this is what we call anonymity. So what I want to show you next is a video of 20 of these little robots flying in formation. They're monitoring their neighbor's position, they're maintaining formation. The formations can change, they can be planar formations, they can be three-dimensional formations. As you can see here, they collapse from a three-dimensional formation into planar formation, and to fly through obstacles, they can adapt the formations on the fly. So again, these robots come really close together, as you can see in this figure 8 flight. They come within inches of each other. And despite the aerodynamic interactions with these propeller blades, they're able to maintain stable. So once you know how to fly in formation, you can actually pick up objects cooperatively. So this just shows that we can double, triple, quadruple the robot's strength by just getting them to team with neighbors, as you can see here. One of the disadvantages of doing that is as you scale things up, so if you have lots of robots carrying the same thing, you're essentially effectively increasing the inertia, and therefore you pay a price. They're not as agile. But you do gain in terms of payload carrying capacity. Another application I want to show you, again, this is in our lab. This is work done by Quentin Lindsay, who's a graduate student. So his algorithm essentially tells these robots how to autonomously build cubic structures from truss-like elements. So his algorithm tells the robot what part to pick up, when, and where to place it. So in this video you see, and it's sped up 10, 14 times, you see 3 different structures being built by these robots. And again, everything is autonomous, and all Quentin has to do is to give them a blueprint of the design that he wants to build. So all these experiments you've seen thus far, all these demonstrations have been done with the help of motion capture systems. So what happens when you leave your lab and you go outside into the real world? And what if there's no GPS? So this robot is actually equipped with a camera and a laser rangefinder, laser scanner. And it uses these sensors to build a map of the environment. What that map consists of are features like doorways, windows, people, furniture, and it then figures out where its position is with respect to the features. So there is no global coordinate system. The coordinate system is defined based on the robot, where it is and what it's looking at. And it navigates with respect to those features.
So that's SLAM.
So I want to show you a clip of algorithms developed by Frank Shen and Professor Nathan Michael that shows this robot entering a building for the very first time and creating this map on the fly. So the robot then figures out what the features are, it builds the map, it figures out where it is with respect to the features, and then estimates this position 100 times a second, allowing us to use the control algorithms that I described to you earlier. So this robot is actually being commanded remotely by Frank, but the robot can also figure out where to go on its own. So suppose I were to send this into a building and I had no idea what this building looked like, I can ask this robot to go in, create a map, and then come back and tell me what the building looks like. So here, the robot is not only solving the problem how to go from point A to point B in this map, but it's figuring out what the best point B is at every time. So essentially it knows where to go to look for places that have the least information, and that's how it populates this map. So I want to leave you with one last application. And there are many applications of this technology. I'm a professor and we're passionate about education. Robots like this can really change the way we do K through 12 education. But we're in Southern California, close to Los Angeles, so I have to conclude with something focused on entertainment. I want to conclude with a music video. I want to introduce the creators, Alex and Daniel, who created this video. So before I play this video, I want to tell you that they created it in the last 3 days after getting a call from Chris. And the robots that play the video are completely autonomous. You will see 9 robots play 6 different instruments. And of course, it's made exclusively for TED 2012.
Mr. James Bond thing. Very nice, huh? So this one is similar. You can go to the link.
Let me introduce to you ReZero. This little fella was developed by a group of 10 undergraduate students at the Autonomous Systems Laboratory at ETH Zurich. Our robot belongs to a family of robots called ballbots. Instead of wheels, a ballbot is balancing and moving on one single ball. The main characteristics of such a system is that there's one sole contact point to the ground. This means that the robot is inherently unstable. It's like when I'm trying to stand on one foot. You might ask yourself, what's the usefulness of a robot that's unstable? And I will explain that in a second. Let me first explain how ReZero actually keeps his balance. ReZero keeps his balance by constantly measuring his pitch angle with a sensor. He then counteracts and avoids topping over by turning the motors appropriately. This happens 160 times per second, and if anything fails during this process, ReZero would immediately fall to the ground. And to move and to balance, ReZero needs to turn the ball. The ball is driven by 3 special wheels that allow ReZero to move into any direction and also move around his own axis at the same time. Due to his instability, ReZero is always in motion. Now here's the trick. It's indeed exactly this instability that allows a robot to move very dynamic. Let's play a little. You might have wondered what happens if I give the robot a little push. In this mode, he's trying to maintain his position. For the next demo, I'd like you to introduce my colleagues, Michael on the computer and Thomas, who's helping me on stage. In the next mode, ReZero is passive and we can move him around. With almost no force, I can control his position and his velocity. We can also make him spin. In the next mode, we can get ReZero to follow a person. He's now keeping a constant distance to Thomas. This works with a laser sensor that's mounted on top of ReZero. With the same method, we can also get him to circle a person. We call this the orbiting mode. Alright, thank you, Thomas. Now, what's the use of this technology? For now, it's an experiment. But let me show you some possible future applications. ReZero could be used in exhibitions or parks. With a screen, it could inform people or show them around in a fun and entertaining way. In a hospital, this device could be used to carry around medical equipment. Due to the ballpod system, it has a very small footprint and it's also easy to move around. And of course, who wouldn't like to take a ride on one of these? And these are more practical applications, but there's also a certain beauty within this technology.
Otherwise, you would go with the four-wheel vehicle. And the hospital application is really a good one because you can have a patient with an IV, and essentially this is walking next to the patient. So it's a very complicated machine. You have to build something like that. All right. So I just wanted to give you this idea that localization doesn't have to be absolute. It can be with respect to another object. Okay, now we'll do odometry and then we'll probably call it a day. I don't know how many more slides are left here, but So localization using odometry. We've talked about this before, but you just accepted what I said that odometry is not accurate. Now you'll see data to support that. So odometry uses wheel rotation sensors to estimate position. IMU is the same. So an IMU device is one that can measure acceleration in the three directions, and then you integrate once to get velocity, you integrate a second time to get position. But because the accelerometer data is noisy, that will also let you down, just like odometry. After a while, you'll not be able to say where you are. Odometry as well as IMU, the readings are accumulated. That means from where you started, you keep adding it to each time you obtain an odometry, it sits on top of the previous value. So it's relative. Odometry is relative. That's why I told you that you can reset odometry, but that reset odometry topic does not seem to be working for Turtlebot 3 for most of the robot sensors, because essentially it zeroes out everything. Okay, why do you get error? I mentioned this yesterday, because you cannot put an infinite number of ticks in that optical wheel that is attached to the the moving wheels. You can put 10,000, 20,000, but you can't have infinite resolution. Therefore, in between one encoder tick and the next, you're in no man's land. You don't know exactly how much you moved, right? So because of that, it causes an error. Wheel mismatch, tires inflated to different pressures, definitely a problem. Slip. It slips, maybe the ground is a little bit smooth, so you're going to have a problem. So the position error, actually it keeps on adding to itself. It doesn't cancel out, it keeps on adding. And unless you have something else correcting it, like GPS, Or like in SLAM, you look at the obstacles and that's an independent reading. The estimate will gradually become useless. So the best analogy is, remember I said that odometry is like counting your own steps. So if you went 100 steps, you're blindfolded, you can't see anything, right? Because if you can see something, you change your steps to get to the same point. But if you're blindfolded and you're asked to walk 100 steps, you'll end up in different positions each time you do it. Maybe if you're tired, you're going to take small steps. So all those play a role. So a blind person, right? How do they move around the house? Because they know precisely where all the furniture is. They learn it. And so they grab the refrigerator handle and they know, okay, I made it there. So they approximately count their steps. And then they grab something that they know, the knob of the bathroom door, etc. So there are 3 types of errors in odometry. Range error, that means the total distance traveled. This is the most favorable to you. The range error typically will not be off by much. It is the one that hangs on the longest. So the range error falls apart the slowest. Turn error is one of the worst, because if you think you're here and you're actually here, that's it. You cannot recover from that error. There's no way. If you think you're here but you're actually here, it's over. And as you go, it actually builds up more and more. Because imagine, if you think you're going here but you're actually going here, then these 2 lines are going to diverge. And there's no way of recovering. That's why you need correction. You need GPS or something to reset you. And drift error is because of the turn error building up. Basically drift error is not a new type of error, but drift error results from turn error estimate. So I think I mentioned yesterday why this is called dead reckoning. It's because you're measuring yourself in order to figure out where you are. So you're measuring your own steps. We're not going to go through this. You can, the links are there. You can go look at it, and we don't want NPR yelling at us. Okay. So this was a study conducted on odometry. It's cited on page 270 of this book by Roland Sequard, and the results are actually here. So in one experiment, what they did was they made the robot go straight. You're familiar with the Gaussian, right? Mm-hmm. So the Gaussian represents uncertainty. So a one-dimensional Gaussian looks like this. This Gaussian has a mean of 0. It could be any mean actually, and it has a standard deviation of this much, 0.3413. Okay. So another name for the Gaussian is the bell-shaped curve or the normal curve. Multiple names, and essentially it always looks like this. If it is taller, it is narrower. If it is shorter, it's broader. So if it is shorter and broader, it means you have more uncertainty of the quantity. If it's tall and sharp, you have more certain. More uncertainty, less uncertainty, right? So that's a one-dimensional, but this is a two-dimensional Gaussian. So x and y, you have to have a two-dimensional Gaussian. And similarly, there are three-dimensional Gaussians. Three-dimensional Gaussians, you can't even plot it, right? You have to imagine it. Because how can you plot a three-dimensional Gaussian? You can't. So two-dimensional is the best you can do. So here, the growth of the post uncertainty for straight line movement. You're asking the robot to go straight. It's like you're asking the person to go straight 500 steps. Note that the uncertainty in y grows much faster than in the direction of motion. That is because of the turn error. So this way, your range error is quite okay. It's not so bad. That's indicated by. So by the way, you're wondering where did this come from? So you can take this Gaussian, and if you section it, right? If you section it, you get an ellipse, right? And what we are plotting is a section, because how can they show the Gaussian there? Yeah. So what they're doing is they're showing a section of the Gaussian in order to convey whether it's uncertain, more uncertain, or less uncertain. So essentially, they're taking a section of the two-dimensional Gaussian and showing it here. I think this may be like 3 sigma or something. I don't know what. Oh, somewhere here they say, yeah, 3 sigma. Here it is. The ellipse drawn around the robot position represent the uncertainties in the xy direction, 3 sigma. So 3 sigma, they're cutting it. And notice again that the uncertainty grows more in this direction, perpendicular to the motion. This way, it's holding steady. The range error is least. Turn error is going to kill you. So this is going on a circle, a well-known circle motion, right? This is going on a circle. And this time, there are some strange results. Again, the uncertainty grows in this direction more than in this direction. But unlike what you might expect, this is not perpendicular to the direction of motion. It's slightly tilted. And of course, the question is, why is it tilted? Well, you have to go read that study. I don't know why. You have to see exactly why this does not point towards the center of curvature. Why are they all, slightly different? Why are they not perpendicular to the path? He mentions this here. Note that the main axis of the uncertainty ellipse does not remain perpendicular to the direction of motion. You have to go look at the study in order to figure that out. But basically, the range error is okay, but the perpendicular error is killing you. So, therefore we need help. Because if we depend on odometry for too long, you'll be completely lost. You could be anywhere. Basically, what this means is, you could be anywhere. See, this ellipse is growing and growing and growing, and eventually, you could be, so the Gaussian is getting shorter, but it's getting wider. And eventually the Gaussian will get washed out, which means that you could be anywhere. And you don't want that. Therefore, you want to refresh. So what does a blind person do? Hopefully they find something familiar, like a couch. So that's why you never rearrange the furniture in a blind person's house, because it is set up to help them move around. Nowadays they may have electronic help. I'm sure they have some devices to help them move around. But therefore you go odometry plus GPS. That's one way of using. Outdoors most of the time you're going to do that. IMU plus GPS is preferred for skid steer vehicles. For skid steer vehicles you cannot use odometry, because the moment you slide on the ground, the odometry values are pretty much useless. Or you can do odometry plus LiDAR, that is the SLAM mode. Right? And remember Bluetooth and all that, there were many options. One of the things I want to point out about those two videos is, so universities get to do that all the time. They do fun projects that may not have any immediate product implication. So they just do things because they're trying to discover stuff. Only a university can do that. Companies don't want to spend money on things that don't become a product. So that's why companies and universities, they work well together, or should work well together, because in universities you kind of don't focus on a product. You just do things just to discover things. So work on that exercise. I think it will benefit you a lot. You'll have a feeling of achievement if you can do it. I've given you all the hints again. So let me just repeat. You have a for loop which goes as many times as you have waypoints. So I've given you 3, right? You can make it 5, 6, 7. Once it works, you can play around with it. Alright? Then you have a loop that is checking whether you're within that circle. Right? Then you have another loop within that where you're checking whether you're pointed towards the next vertex. And remember all those little things like quaternions to Euler conversion, heading, prevent, wrap, like try to unwrap it. So all those other 2 programs are useful because you'll have to borrow some of that code. So just check the code as you go. You never write a big program and then you say, okay, let me debug it, because you don't know where to start. So check each part of the code, and then you asked for the approximate value of KP. I said it's 0.01 or something in that neighborhood. Because if you put 1, robot goes like this. And then you start saying, okay, you start questioning your whole algorithm. But if you formed up the other algorithm, then you know it's got to be this, and you just change it. If you have mistakes elsewhere, this is not going to do anything, right? So it could be some other mistake, but typically, if you fixed everything else, you dial down the KP value, and you'll find it works perfectly. So if you can't get it, I'll show you my program next week.